Hello everyone and welcome to today's lesson. Before we move on with today's topic, let's go through the solution to last week's problem. The question was, with the function of x of e, x cubed plus 2, what is the derivative? Okay, so here we have the question, and we're going to use the first principle or the derivative law right there. So the law, the general formula, function of x plus h minus fx over h. So we take this equation here and we put these values into here. So what we have is x plus h in brackets to the power of 3, okay, the 3 there, plus 2, and then you minus fx minus x3 plus 2, x to the power of 3 plus 2. All of that over h. When you expand that, x plus h times x plus h times x plus h, you get x cubed plus 3x squared times h plus 3x h squared plus h to the power of 3 plus 2, take away x to the power of 3 minus 2 over h. And then we simplify this. Okay, we put the common terms. We put that x3 with that x3, the negative 2, that plus 2. So those cancel out, and we get 3x squared h plus 3x h squared plus h cubed over h. Now from there to here, what we've done is we've factorized. Okay, remember that word? We factorized the common factor, which was h, so we took h from here, h from here, h from here, and we put it outside of the brackets. And now what we can do here is that h can now cancel out with that h, and you get 3x squared plus 3xh plus h squared. When you get to this point, this is a point where we can now substitute, we can now input this value of h as h approaches 0, the function of x is 3x squared. So if that's 0 here, that whole value becomes 0. And if that's 0, 0 squared equals 0. So all of that cancels out. So the function fx of x cubed plus 2, when we the derivative of that is 3x squared. Okay. Remember our shortcut method we had talked about last week? Take the 3, put it there, becomes 3x. A constant becomes a 0. Remember that law? And then that is minus 1. 3 minus 1 equals 2. 3x squared. Okay, let's move on. Our key terms for today: differentiation, a function, factorize, the slope or the gradient, which is m. Remember that? An optimal solution, the derivative, as we just talked about, power or exponents, rectangular, a range or an extent or a limit, and a diagram or a graph. So today's topic, differentiation, part 2. Remember, differentiation is also known as differential calculus, and today we'll be talking about mainly about graphing and optimization, an introduction to graphing and optimization. Okay, remember we talked about differentiation being about finding the derivative. So the derivative of a function is the slope at a given point. So here's an example. We have the curve there. Say that y equal to the function of x. And maybe we have some curve going like that. So say this point, this is called a tangent. Another line there, and that's 90 degrees. And what we do with that, we find the gradient of that line, so y and x, and the slope of that line is the derivative of this function at that point. Okay, at that point only. So again, here's a linear segment of the gradient. We've done this before. So you have a curve, a line, you get the tangent, remember that's 90 degrees, and that line, this point, any point here, a point up here and a point up here, that will be x1, y1, and that'll be x2, 2y2. So the gradient will equal to, where is this? y2 minus y1 over x2 minus x1, or take away x1. And that gradient, is the derivative, dash or dy over dx. Okay, let's move on. Again, the symbols for finding the derivative. Okay, we have dy over dx, or you can have f prime or dash x. And here's another way, it's not very common that way. df of x over dx. So by definition, dy over dx with respect to x is equal to delta y, which is y2 take away y1, over the change in x, or delta x, which is x2, x1, and that is all equal to, that's the gradient as mentioned earlier. Okay. Another way to view the derivative or derived function of fx denoted f dash or f prime x, f dash x, is defined as, remember our derivative law, the first principle, f prime x is equal to the limit as h approaches 0, fx plus h minus fx, or the function of x, over h, And by definition, if you look here, you have x plus h here, x, and that is equal to h. So fx plus h minus that, you get that. Okay? You get the distance from here to here. That, take away that, equals that. So this is also comes to the gradient. The gradient of P to Q is equal to fx plus h minus fx over h. So the gradient is the same as finding the derivative. In Leibniz notation, f prime x as a limit of h approaches 0, you can write it that way. The derivative of y with respect to x. Okay? Sounds confusing? Let's go through some examples. Okay, so let's have a look at this graph here. You can see that blue line. We have an example, y is equal to f to the power of x, this equation. So the derivative is the slope of the original function. So the derivative is equal to m. Now let's have a look at the first part, that first line. Remember our formula for the gradient, delta y over delta x, which is equal to y2 minus y1 over x2 minus x1. So there, the change in y, that would be 2 minus 0 over 1 minus 0, which equals 2 over 1, which equals to 2. So that's how we have 2 here. This is the derivative here. That's why f of x, and this is, the derivative is 2. Notice it's a straight line, so it remains at 2. Okay, coming down. The next section, the gradient is 3 minus 2, that's 1 over 1 to 3. That equals to 1 over 3, and that's how we have this part here. So the gradient, a smaller gradient, goes across until 4. And then the next part, the gradient is 0. Okay, that's why it's all in a line, going straight across. Why is it 0? See that straight flat line there? So what we have, using this formula over there, is 3 minus 3 over 6 minus 4, I believe, which is equal to 0 over 2. So 0 divided by any number equals 0. That's how you have the 0 here. And the final part, notice that the line goes downwards, so it's going to be a negative gradient, okay, if the line goes down. So we have 3 over 3, which equals to 1. It's going to be a negative 1. To prove this using the formula, we can take, what do we have? 0 minus 3 over 9 minus 6, which equals to negative 3 over 3, which equals to negative 1. And that's the negative 1 here. So all these are the derivatives of that line, of that function. Okay, let's move on. Okay, similar to our example that we just did, instead of having straight lines like we just had, now we have a curve. So we have a curve going up. So that's f of x, and our job is to find the derivative. So what is f of x? So as you move down, the equation for that parabola is y equals x squared minus 3. So you can use this the derivative formula, and you find out that the derivative coming from here to here is of x squared minus 3. The derivative is, take that 2, put it there, 2x. As simple as that. Or you can use this formula here, like we just did earlier on, in the 0, 2x here. Therefore, any value of x, the derivative, all you have to do is multiply by 2. So for example, at x equals negative 3, that's x times 2, 2, 3 equals negative 6. And that's how you have your negative 6 here. Or we can take this one, so 1, see the 2x for the derivative, multiply by 2 equals 2. So at that one, you got 2, where is it? Over here. That 2 there. Let me rule it straight. Negative 6 on that one. Go on 0. Yeah, you got 2 here. Negative 6 here. And so forth. So if you take each of these values of even 0, sorry, let's just do 0. 2x, if x is equal to 0, 2 times 0 equals 0. So therefore, at x equals 0, the derivative on the y-axis is 0. You can take all those lines and you'll find out if you connect each of the points from the derivative, you get a straight line. And this is the line of 2x. Okay, y dash, where is it? Y dash x is equal to 2x for the original function x squared minus 3. Okay, let's move on. Now let's move on to optimization problems. Optimization problems are problems that ask for the most efficient or best solution. They appear in many forms and usually ask to find a maximum or minimum, okay, or minimum amount. Quite often the question can be misleading or seem confusing, so you have to pay careful attention. We need to pay careful attention. What we should do when solving these kinds of problems, read the question at least twice. Draw a diagram or graph where appropriate. This should help you introduce any variables you are likely to need. It may be that you come back to the diagram to add in an extra x, etc. So what this simply means is it makes it much easier to understand if you actually draw some picture, a diagram, a graph. Try to translate any information in the question into a mathematical statement. So you're going to have formulas like therefore x, 2x plus 3 is equal to y, okay, for example. Identify the variables to be optimized and then express this variable as a function of one of the other variables. So the keyword here, variables. Our two variables, x and y, we need to pay careful attention to what we're trying to find. Is x a min or a max, for example? Right? So let's go through an example. Example, an open box with a rectangular base is to be constructed from a rectangular piece of card measuring 16 centimeters by 10 centimeters. A square is to be cut out from each corner and the sides folded up. Find the size of the cut out squares so that the resulting box has the largest possible volume. Okay, how can we get the largest possible volume? Okay, let me just give you a quick example. Imagine this is a card, okay? It's straight So we're going to cut each of the corners out, and then we're going to try to fold it. Okay, you try to cut out each of these sides, and then you fold it to make a box. So we're trying to make a box. Okay. Okay, this doesn't work with this. Anyways, therefore, what we notice is that we have a range of x being between 0 and 5, right? You can't cut all the way here, and you can't go all the way here. 10 minus 2x. So, first thing we do, what is the volume? What's the formula for the volume? LBH, which is to find the volume of a cube, okay, a box or a cube. The volume is the length times multiplied by the breadth multiplied by the height. So going this way, so that multiplied by that, and that, say that's z. 3 variables, LBH. So let's look at the length of the 3 sides. That side would be equivalent to 16 minus 2x, because we're going to cut here and there. And that would be 10 centimeters, minus 2x, 1x, 2x. So one side is 16 minus 2x, the other side 10 minus 2x, and for an example, and this would be x, okay? That would be x, and that's x here, LBH, the height is x. What we do now is we're going to find this, we're going to expand this, 16 times 10. Remember the FOIL method we talked about before? Times that, that times that, that times that. Then you expand all of that, and you get 4x cubed minus 52x squared plus 160x. And now here's something we need to take account of. The max or minimum value of v occurs when the dv over dx is equal to 0. What does that mean? So what that means is, once we find the derivative of v with respect to x, we'll use our law, the power rule. So we'll take that, for example, 4x3, take that 3, multiply it by here, that'll be 3, that'll become 2. 3 4s are 12, that's 12x squared. And we do that for 52x squared and 160x. And then we get 12x squared minus 104x plus 160 is equal to 0. We make the derivative equal to 0. Okay, this is for finding an optimal solution. Then we solve. Okay, 12x squared minus 104x equals to 0. Factorize over here. The common factor is 4. 4 times 3x minus 20 multiplied by x minus 2 is equal to 0. So, one sec. Therefore, remember how to factorize that? Therefore, x is equal to 2 or 6 2/3. So you have 2 answers. Okay, you have a quadratic equation there. And then you find out that x is either 2 or 6 and 2 over 3. Now we do something called the second derivative test. So we have, and here's an example. I'll give a quick example here. F dash x, second derivative, 2 dashes, 2 primes. Say for example you have x4, and that becomes 4x3. A double derivative, second derivative, becomes 12x squared. Okay, remember that. So the second derivative test, it's a test. If the second derivative test is greater than 0, then f has a maximum. It's a max. If f dash x is, smaller than 0, it's a maximum. If it's greater than 0, then it is a minimum value. Now, After doing the double derivative test, we get 24x minus 104. So if we take that 2 and put it here, we get 2, that's 48 minus 104. That will equal to a negative, okay? And a negative value is a maximum. And we are looking for, what was the question? We're looking for the maximum volume. So we want a maximum. If we take 6 and 2 over 3, and we put that here, we get 6, 2 6 and 12. We get something like 140 something, take away 1 over 4, which equals to a positive value. Positive equals to greater than 0, and greater than 0 equals to a minimum. So we don't want a minimum, we want a maximum. Therefore, the maximum volume is when x is equal to 2. So you have the best way to create the box in this case is to have 2 centimeters here, 16 centimeters, and 10 centimeters. Okay, that's the best way. Or the optimal solution, or where you get the maximum volume. So today's quiz, here we have a travel graph. Distance on the y-axis in meters, and we have time on the x-axis in seconds. So just imagine this is a car traveling. So after 10 seconds, the car goes 50 meters. After 20 seconds, it goes 100 meters. And then for this 10 seconds, it remains at 100 meters, and so forth. And I've marked some points, 1, 2, 3, 4, and 5. Okay, this is a car traveling through time. So the instructions describe what is happening at each stage of this travel graph. Okay, what's happening at stage 1, what's happening at stage 2, 3, 4, and 5. Finally, thank you for viewing today's lesson. Hope to see you next time with Everyday Seminar.